In this video, let's talk about local linear regression. Comparing to the kernel smoothing method, it just adds one modification to it. So the kernel smoothing method can be thought of as a weighted local average of the data points, where the weight is given by the kernel function. For example, the kernel function can be the probability density function for the Gaussian distribution. So that gives us the weight for the local averaging. The kernel smoothing can be interpreted as an optimization problem where the objective is the weighted square distance from the fitted value to the data points. So let me just write that down. This is the weighted sum of distance square. So the solution to that is a weighted average. So I should emphasize this is at each point x, right? That means at each x, we want to find a constant that is closest to each data point based on the weight. The constant will be the fitted value for this problem, for the kernel smoothing problem. So for the local regression, it is very similar to that, except that we are adding a slope term to this minimization problem. So what does this mean is that this means that at each point x, we have a weighted least square problem, a regression problem. So at each x, we solve a weighted least square problem. Okay, let me just write that down. So when x is fixed, then our objective becomes minimize a and b, the sum of wi yi minus a minus b times x minus xi. So this equation here shows that this regression problem is centered around x. Okay, so if I'm to draw this, this means that suppose here is our data point x, then we are doing a regression using the points of the data, right? So each point will be given a weight, right? So let's say these are weight 1, weight 2, weight 3, weight 4, weight 5. And then what the problem we are solving here is that we want to fit a line based on this weighted least square problem. And you see that this point here, right here, right, the fitted value is A, right? So that's the intercept. And then the slope is given by the B, right? The slope is B. So that is the problem we are solving, but we are solving that at each data point x, and the x can be continuous value taken up at any real number for this problem. Okay, so this also means that our predicted value, so y bar of x, will equals to a of x, right? Because we are kind of centering at each point when we are solving this least square problem. Okay, so now let's just do a comparison between the kernel smoothing method and the local regression method to see what this extra term can bring us. Okay, so I've made this plot to compare between the kernel smoothing versus local regression. So see here that the red curve here is a kernel smoothing, and the blue curve here is a local regression. You see that for the majority of these curves, they look almost identical, right? That means like with or without using the slope, it makes almost no difference. But see, the behavior is very different at the boundary, right? At this part and this part, right? At the boundary is very different. This is because the data points disappeared at the boundary. So that means when we are taking local averages at the boundary, we only got the data from one side. So that's why that's why the kernel smoothing method barely moves, right? It's almost flat in those places. And for local linear regression, it kind of interprets the fitted value as a straight line. So that's why we see the boundary behavior is much nicer for the local linear regression. Okay, and one last thing is that This local regression problem is the same formula is scalable to multi-dimension. So the same problem is scalable to a higher dimension. But one problem is that in higher dimension, the data may be sparser. That is due to the geometry of the high dimensional data set where there is simply too much space between data. So that means the performance of this local regression may not be ideal unless we have lots of data points. Okay, so that's pretty much about this video. And for the next video, let's just compare the local method versus the global method, the span method, to see which is a better method to fit curves in different settings of practical problems.